Okay, good morning to all. Another session, logic design. Hopefully, one of the last sessions we are going to be doing. Of late, we've been talking much about sequential circuits. To be more precise, flip-flops, an element which stores data, flip-flops. We talked of, we began with the RS, latch. We added a clock and we called it the RS flip-flop. We modified it. We got the D, we got the JK. I think last time we were talking about the JK. We introduced the master and slave to as a solution to the racing condition, Today we modify the JK. Today we modify the JK to come up with the T flip-flop. Today we talk of the T flip-flop. In Africa, T flip-flop. So basically the T flip-flop is a modified JK. This is a modified JK to have only the toggling. I think I've been emphasizing on ability to come up with the truth table, characteristics table, and excitation table of all the flip-flops we've done so far. That ability will probably help you get a very good understanding of how you can apply the flip-flops. All right, truth table JK. Truth table JK, we have JK, we have Q next 0 1 0 1 0 0 1 1. When JK are 0, we have the memory. This is the reset 0. This is the set. Here we have the toggle. For the T flip-flop, we only want a case where our flip-flop is in this mode, the toggle mode. And how do we do that? We take our JK with two inputs. So we have Q, let me do this. Outputs Q bar. How do we modify this? JK is equals to 1. This is the toggle mode. So we replace these two inputs with one input, which is the same. And we rename it T. Now when T is equals to 1, it means our flip-flop is toggling, always toggling. Because when it is 1 here, it is 1 here, it is 1 here. It is always toggling. With that truth table for the T flip-flop, the truth table for the T flip-flop. The truth table for the T flip-flop, we have the clock, obviously. The block diagram, we have something like this: T, Q, Q bar. Then we can have a clock for a synchronous sequential circuit. Right. So if the clock is 0, we all know what happens by now. We have the clock, we have the J, no, we have the T. We have the Q next. When the clock is 0, no matter the input, we now know what happens. This is the memory state. Right, when clock is 1, T is 0. What happens here? T is 0. This is another memory state. It's the same as J is equals to K is equals to 0. Memory state. It's the same as R is equals to S is equals to 0. Memory state. It's the same as D is equals to 0. Memory state. Now, when T is equals to 1, this is the state we want. Toggling. And that sums up the truth table for the JK. We can have the characteristics table. I think by now this is simple stuff. Once you know how to come up with one of these, you are home and right. The characteristics table helps us finding what the next state will be. So for inputs J and K and Q, what would be the next state? Where this is your present state. No, this is not JK, this is T. So 0, 1, 0, 1, 0, 0, 1, 1. Participation. What is my Q next? Who do we have here? Johnny Tanaka. TJ. Please unmute yourselves. Class rep, Rombi, unmute yourself. So that we can talk of Q plus. Nope. We have Brian Masunga is there. Christine. Yep. Christine, unmute yourself. Who is here to participate? Nobody wants to participate. Does it mean you don't know or you just don't want to participate? Rafa? No, Rafa, I made you a target last time. I think you do understand this now. Yes or no?
Yeah, I do. I think 0.
Yep. Why?
There is.
Why? That's your reason right there.
It's the memory state.
It's the memory state. Because T is 0, T is 0 memory state. It means whatever state we had here is the same state we have here. I see only these 3 girls to participate for me, please. Rumbizai, Christine, or Tanaka, Johnny. Unmute yourselves. Okay, yellows. Godzi. Adro. Can you please help us?
Yes, sir.
Yes. Do you understand what we are doing here?
Yes, I'm following, sir.
Right.
I think there is
What is the next stage?
The next stage is supposed to be 0.
Nope. Why 0? Here, what is the next state here for 0, 1? If I can be precise. 0, 1, what is the next state? The next state is 1. Do you know the reason why? The reason why is because of this. This is where you look. You look at your truth table. When T is equals to 1, what did we have? We have what we call toggling. What does toggling mean? It means for Q and Q next, if Q is 0 present state, Q next will be 1. That is toggling. Complement, if it is 1, then it will become 0. That's why it's 1 here, because Q was 0, it becomes 1 because of this T is equals to 1. Toggling. We always look at the truth table. Go Z. What will be the next state here? 1, 0. Use the same logic we've been using here. Use the truth table here. Do help me. What will be our next state?
The next state here, it's supposed to be 0
Why 0?
because Q is 1, then the next is 0.
But did you look at this T? You need to look at the T
Yes,
as well. What is T?
T is 0.
When T is equals to 0 here, what do we have?
It's memory.
All right. What does memory mean? It means the state we were in will be the next state. So what will be our next state? Go Z.
Our next state will be 1.
1. Thank you very much. And here, go Z again. Look at Q, look at T, and tell us what our next state will be for 1, 1.
1, 1, it means it will be toggling, so it's supposed to be 1.
If it's toggling and we have a 1 here, what will we have here? This is for toggling. If we have a 1, we will have a 0.
Yeah, the next is 0.
0. Yeah.
Thank you very much. All right, and this is the characteristics table. The same way I'm coming up with this C table for the T flip-flop is the same way you come up with the C table for the D, for the JK, for the RS, for all the flip-flops you will encounter. Then we go to the excitation table. You use the C table to find the excitation table. What is the excitation table? The excitation table shows you what changes you need to make with the excitation table here. Excitation table. And for the excitation table, we have Q and Q next. Then we have T. What changes do you need to make on your flip-flop to get the intended change of states? So in this example, 0, 0, 1, 1. If I want to change, this is not necessarily a change, but if I want my next state to be the same as my present state, 0, 0, what will be my T? You go and look at your characteristics table. From my characteristics table, if I want to go from 0 to 0 here, what is my T? I'm going from 0 to 0 here. My T is
0.
0. And if I go from 0 to 1, it's 1. 1 to 0 is 1. 1 to 1
It's 1.
is 0.
It's 0.
This is how I come up with my excitation table. And I think this summarizes everything we have on flip-flops. Flip-flops basics, a memory element. We started with sequential circuits. What are sequential circuits? Circuits with memory elements. What makes up that memory element? What stores data? What stores data is a flip-flop. We have different types of flip-flops. JK, it stores data. D, it stores data. It depends on how you want to apply the flip-flop. D, we have T. We also have RS. What you need to know about this, you need to know the truth table. You need to know the characteristics table. You need to know the excitation table. Once you know these three, then you can apply them. They have many different applications. And this is my next. This is the next thing we are going to talk of. Applications. How do we apply? Now let's apply those memory elements. Applications. Application number 1. We have application of the flip-flops in frequency division. Frequency division. A frequency divider. What is that? Suppose you have a clock of frequency, let's say 10 megahertz. That is the frequency you have. That is the frequency you are given. But maybe the equipment you are using, it only allows you to use a frequency of 5 megahertz. How do you find the 5 megahertz out of this? You can use a frequency divider, which divides your given frequency by 2. This means I'll get 5 megahertz. Provided 10 megahertz, I can find 5 megahertz. How? By using a frequency divider, f over 2. How do I do that using the flip-flops? How do I do that using the flip-flops? We have a frequency divider by 2, which is made of a D flip-flop. Basically, it's like this. Now we are applying these flip-flops. So D, Q, Q bar. So this is my input. Then I have my clock, positive age. This is my clock. This is my input. This is my output. Then we have this output being fed into D. What we have there is a frequency divider by 2. Now, how does it work? I'm going to demonstrate how it works using clocks. Let's say, for example, I have a clock. This is my clock. And voila. This is the input of my clock. Now, suppose my Q initially is a 0. Suppose my Q initially is a 0. It means my Q bar initially is a 1. Because Q bar is the complement of Q. Suppose my Q initially is a 0. Q initially is equal to 0. This means Q bar is equal to a 1. All right. What will be my D initially? What will be my D? If I look at this diagram, my D is equal to Q bar because Q bar is being fed back into D. So D and Q bar is the same. We have a 1 here. Now, when does the state change? I look at my clock. This is a positively aged triggered, positive age triggered clock. So it means every positive age, there should be a state change. This is a positive age. This is a positive age. This is a positive age. A positive age. It means at this point, there should be a change in state. Change in state. At this point, change in state. Change in state. All right. So my Q initially is a 0. When it reaches this point where it needs to change its state, how does it change? I look at the characteristics. Let's begin truth table of a D flip-flop. truth table of a D flip-flop, I have my inputs Q, D. What will be my Q next? 0, 1. Let me remove this. If my D is equal to 0, what will be my Q plus for the D flip-flop? Truth table, D flip-flop. Anyone with a good memory? 1 here.
It should be 1. Yeah, exactly.
Are you sure?
Yes.
And what's the name of the state? What's the name of this state? We have reset, set, memory, toggle. What's the name of this state?
Toggle.
Nope. With the D flip-flop, we don't have the toggle state, do we? Nope, we don't. With the D flip-flop, we have this state, the memory. Here we have a Q. Let me see.
1.
Nope. Let me put the clock here. The clock produces the memory. Let's put the clock. So when the clock is 0, whatever we have here, we have the memory state. When we have a 0 here, we have the reset state. When we have a 1 here, we have the set state. This is what we have with the D flip-flop. No toggling, memory, reset, and set. All right. So when our clock is 0, we have the memory. When our clock is 1 and our D is 0, the reset. Clock 1, D1, we have the set. How do I apply that on the frequency table? All right. Let's begin here. My Q is 0 initially. When it's time to change its state, what happens? I look at D. What is my D? Initially, D is a 1 here, 1 here, 0 here. When it's time to change state, I look at my D. My D initially is a 1. If my D is a 1 and my clock is a 1 as well, what do I have? I have the set state. So it means my Q,
It's 1.
my Q changes from 0 to 1.
1.
At this point, the clock is 0. When the clock is 0, what does that mean for my Q? It means my Q is in the memory state, my Q next. So it remains as 1, memory state. I do the same for Q bar. Q bar is just the complement of Q. So here I had 1. When Q goes to 1, Q bar goes to 0. What happens to D? D is goes to Q bar. It also goes to 0. Everything has happened sequentially. I started with the 0 here. It means I had a 1 here. So as soon as the clock hits the positive edge, it means I have a 1 here because Q bar is a T. Once I have a 1 here, there is a change. This state, the set state, it means my Q changes to 1. Next state. When my Q changes to 1, my Q bar changes to 0. When it hits the next change of state, I have a 0 here. It continues. This is now what will be happening. So at this point, another state change. I look at D. What is my D? My D is a 0 here. If my D is a 0, I have a reset. I go back to 0. When my clock is a 0, here I have a memory. It remains as 0. Next state change. This becomes a 1 because it's the opposite. This becomes a 1 is equal to Q bar. Next state change on my Q. D is equals to 1. It goes up, memory, and it continues like that. 10 minutes. And this continues, this continues, this continues. But what do I have? Frequency. If I started with 10 megahertz, this is my clock. I started with 10 megahertz. What will be the frequency of this output? So if my frequency is 10 megahertz, then my T here, F is equals to 1 over T here. What is this time? This is 1 over 10. All right. This is T. It's equals to 1 over 10, which means F will be equal to 10. F is equals to 1 over T. But what happens to Q when I use this D flip-flop? What happens to Q? My T changes. It changes to what? It changes to this. What is this? What is this? 1 over 10.
1 over 2.
1 over 10 plus 1 over 10. What is that? 2 over 10. All right? This becomes 2 over 10. True or false?
It's true, sir.
Right. So now we have a 2 over 10 as my new T. If my T new is now 2 over 10, which is 1 over 5, it means my frequency is 5 megahertz. And I've applied a D flip-flop to divide a given frequency. This is how application of the D flip-flops is. We can do the same. Say if I want to divide this 10 maybe by 4, I can just add another D flip-flop. I can add another D flip-flop. So you see, if I have something like this, this always goes back in here. I have my clock. I have my clock. This is my input. So this is D, D, Q, Q bar, output here. All right, if I have something like this, the output here will be a frequency divided by 4. If I add another one by 6, and just like that. Application of D flip-flops in the frequency divider. This is one of how you can apply. This is why we are doing these flip-flops. Another application, we have what we call registers. Another application, we have what we call registers. Application of flip-flops. Right, we know that one flip-flop, it can store 1 bit. 1 bit of data. If I want to store, let's say this is a D flip-flop. If I want to store a 0 in a D flip-flop, I just put my initial state, D is equals to 0. Then the D is stored in here because the output will be 0. It means I've stored 1 bit of data. But what happens if I want to store more than 1 bit of data? If I want to store more than 1 bit of data, I now have what I call a register. which stores n bits of data. N can be 2, 3, 4, etc., etc. We have many types of registers. Want to note? We will talk of shift registers. To note, we will talk of shift registers, and we will see how do we apply the knowledge we have of our flip-flops in the shift registers. I'm going to start shift registers in the next session. I only have 4 minutes, 20 seconds left. This is for questions and comments on the frequency divider, if any. Four minutes for questions so that I can start shift registers on a new session. No questions, no comments. Then I conclude this by putting emphasis on this. If you know this, the truth table, it means you can come up with something like this. When you come up with something like this, then you understand how you can apply a flip-flop in whatever you want to do. If you understand the truth table, the characteristics table, maybe the excitation table, you can then come up with a way to apply those flip-flops to a given problem. The problem here in this case, we wanted to divide the frequency of the clock by 2. How do we do that? Application. Right. Thank you very much. Join me in the next session soon after, where we discuss shift registers and possibly application encounters as well.